Chapter 7 from Electricity and Electronics in its entirety, including lessons, questions, answers, and explanations. Text by Garish, Duggar, and Roberts. 10th edition. Edited, explained, and narrated by
Hector Vladimir.
Parallel circuits. The objectives for this chapter are to determine the total resistance of a parallel circuit, to determine the voltage drop in a parallel circuit, to determine the current values of a parallel circuit, to determine the wattage values of a parallel circuit, to apply Ohm's law to solve for unknown voltage, current, and resistance in a parallel circuit, to apply parallel circuit theory to assist in troubleshooting in a parallel circuit. Keywords for this chapter include branch circuits, branch currents, mainline current, the reciprocal, the Kirchhoff's current law, parallel circuit. 7.1 Parallel circuit principles. In simple terms, a parallel circuit provides two or more paths for electron flow through a circuit. Look at figure 7-1.
Take note of how each of the three resistors
Are connected to the source with each electron flow path independent of the other. When three resistors are connected in series and one resistor is removed, the entire circuit appears to be dead and the electrons cease to flow. There is no complete path for current. If the same three resistors are connected in parallel, one of the resistors can be removed from the circuit without stopping the flow of electrons in the circuit. This unique condition of the parallel circuit
is the basis
of the first parallel circuit formula that we will study. The parallel circuit voltage. The voltage in a parallel circuit is equal to the source voltage of two or more components are connected to the source in parallel. The voltage drop across each component is equal to the source voltage.
The formula
representing the voltage condition of a parallel circuit in words is the total voltage is equal to any individual voltage drop in the parallel circuit. The formula could be written
as shown,
where N is the total number of voltages, that is
E
total or voltage total equals voltage 1, voltage 2, voltage 3,
and so on.
In figure
7-2,
there are three resistors connected in parallel. A 6-volt
E
source is connected to the circuit.
Each
resistor has a full voltage
potential applied across it.
Each resistor voltage is equal to the source voltage. Parallel circuit current. Current in a parallel circuit follows some simple principles. These principles are summed up in the Kirchhoff's current law. Kirchhoff's current law states that the algebraic sum of all currents entering any point will equal the sum of all currents leaving that point.
Simply stated,
the current flowing into a junction of parallel resistance is equal to the current flowing out of the same
junction.
This leads to the conclusion that the total current in a parallel circuit is equal to the sum of the individual currents caused by each individual resistance. The individual currents are called branch currents. The total current is called mainline current. This is shown in figure 7-3. Since the total current in a parallel circuit is equal to the sum of the branch currents caused by each individual resistance, the formula can be written as seen on the screen, where N is the total number of currents. Work through the circuit shown in figure 7-3. You can see that the sum total of the three individual resistor currents equal the total source currents of 9 amperes. Parallel circuit resistance. When resistors are connected in parallel,
the
total resistance of the parallel circuit is always less than the smallest resistance in the parallel group. In other words, if a 6 ohm and a 4 ohm resistor are connected in parallel, the total resistance will be less than 4 ohms. This principle is extremely important and should be memorized. There are several methods to determine the total resistance of a parallel circuit. These methods include the product over the sum method, the reciprocal method,
the equal resistances method,
and the graph method. The product over the sum method, shown on your screen, is used as a quick way to solve for the total
resistance
when there are two resistances of an equal value connected in parallel. The product over the sum method derives its name from the mathematical terms used in the formula. Product is the term used for the answer to a multiplication problem, and the term sum is used for the answer
to an addition question.
The formula for this method is written
as shown.
Follow the equation. In figure 7-4, a 3 ohm and a 6 ohm resistor are connected in parallel. The total resistance for the circuit is 2 ohms. The reciprocal method. The reciprocal method can be used to find the total circuit resistance when there are 3 or more resistances connected in parallel. The reciprocal method gets its name because the reciprocal of the resistance values is used in finding the total resistance. A reciprocal of a number is equal to 1 divided by that number. For example, the reciprocal of 2 is 1 over 2, or 1 divided 2. The reciprocal of 3/4 is 1 divided 3/4,
which ultimately gives you 4 over 3.
The formula used for the reciprocal method is shown, where n
Equals
the total number of resistances. Notice that when using the reciprocal method,
each
the resistance value is expressed as a fraction. The resistance value is reciprocal. The number 1 is the numerator for the fraction, and the value of individual resistance is the denominator. Figure 7-5 has a 4 ohm and a 6 ohm and a 12 ohm resistor connected in parallel.
Since
the values are expressed as fractions, a common denominator must be found. Then the values can be added together. The common denominator
is 12
for this problem. The total resistance is equal to 6 over 12. The 6 over 12 is the reciprocal of the total resistance. The fraction is inverted, and 12 is then divided by 6 to find the total resistance of the total resistance value of 2 ohms, or 6 divided 12. The reciprocal is 12 divided 6,
which equals to 2.
and that's your total resistance. Unfortunately, most circuits do not have resistance values that lend themselves as neatly as our example to using this method of solution. However, the reciprocal method can be used in these messy situations by converting
individual values to decimals.
In figure
7-6,
resistors of 35, 18, and 7 ohms are connected in parallel. The problem is set up exactly as before, but we simply use a calculator to convert each fraction into a decimal number so that they can be added together easily. The 3 resistor values total to 0.2271. The combined total of the 3 individual resistances
is
the reciprocal of the total resistance value of the circuit. The total resistance is equal to 1 divided by 0.2271, or 4.4.
The equal resistances method.
When a parallel circuit consists of 2 or more resistors of equal value, the total resistance is equal
to the
value of any resistor divided by the total number of equal resistors in that parallel circuit. The formula is shown on the screen, where n is equal to the total number of resistances. In figure 7-7, the 3 12 ohm resistors are connected in parallel. The total resistance for the circuit in figure 7-7 is 4 ohms, or 12 ohms divided 3 equals 4 ohms. Note that the equal resistances method can be used in combination with other methods to simplify calculations. If any number of resistors are of an equal value, but not all of them, the equal resistances method can be used to produce an equivalent resistance from the equal value resistors. For example, you have a circuit with 10 resistors in parallel. 8 of the resistors have a value of 80. The other resistors have values of 20 and 40. How do you find the resistance? Rather than having to total resistance equation for
10
reciprocals, the 8 like valued resistors can be turned into one equivalent resistance. 80 ohms divided by 8 produces an equivalent resistance of
10
ohms. Now add the 2 other resistors to your equivalent resistance using the reciprocal formula.
The graph method.
It's an interesting method of estimating the value of total resistance. The values of 2 resistances are expressed on a bar graph, like the one shown in figure 7-8. A line is then drawn from the base of the first resistance to the top of the second resistance. A second line is then drawn from the base of the second resistance to the top of the first resistance, making a crisscross.
The
total resistance value of these resistances may be read where the 2 lines intersect. A third resistance may be added, and the process repeated. This method is not considered to be very accurate, but it is a quick and easy method to check your work. Power in a parallel circuit. The total power consumed in a parallel circuit is equal to the sum of all of the individual powers in the circuit. The formula is written as shown on the screen, where n is the total number of powers. In figure 7-9, you can see that the total power consumed is 72 watts. Is equal to the sum total of the individual electrical power units, such as R1, resistance 1 equals
12 watts,
R2 equals
32 watts,
R3 equals
24 watts,
consumed at each resistance. And now we'll review questions for section 7.1.
First question. If the source voltage
in a parallel circuit is equal to 10 volts, what is the voltage drop across that resistor R3? Assume that R3 is equal to 50 ohms. For that, we draw the circuit over on the right side of your screen. Answer for question 1, where the total voltage is 10 volts. And we know one of the resistors
value
R3 equals to 50 ohms. So since the voltage drop at each resistor must be the same throughout the series circuit resistors, then total voltage drop equals 10 and R3 voltage drop equals 10, since they must be the same. So we can use that to find out what the voltage is at R3, and we know that it's 10 volts.
Question number 2. A circuit containing 3 resistors in parallel
has a branch current of 3 amps, 5 amps, and 10 amps. What is the main line current in the circuit? Remember, the main line current is the total current. Using the formula for parallel circuit current, where current total equals current number 1, current number 2, and current number 3, meaning at each branch, then we can add what we have already been shown, 3 amps, 5 amps, and 10 amps, which equals 18 amps for current total or mainline current. 3. List 3 formulas that can be used to find the resistance in a parallel circuit. The formulas are shown on the screen. Number 3 on the right side, where resistance total equals resistance 1 times resistance 2 divided by resistance 1 plus resistance 2,
which is the
product over the sum formula.
This is for
2 resistances only.
If you have more than 2 resistances of different values,
you can use the second formula, the reciprocal formula
for resistance,
or 1 over R total equals to 1 over R1 plus 1 over R2 plus 1 over R3,
etc.
If you have 2 equally valued resistances or more than 2 equally valued resistances, you can use the resistance formula, the third one shown, which is resistance total equals to resistance divided by the number of
resistance values.
Remember, these have to be equal. Doesn't matter how many, but
they have to be all the same.
Question 4. What formula for finding the total resistance in a parallel circuit will work
with
any number of resistance values or any number of resistors? And that would be the reciprocal of resistances formula
shown
in number 4 on the right side. Question 5. A parallel circuit has 2 resistors. Each consumes
6 watts.
Calculate the total power for the circuit.
So if you have 2 resistors
in parallel and they both consume each
6 watts, we're talking about power.
We have the power formula, which power total equals power at resistor 1 plus power at resistor 2, etc. So we simply add
6 watts
plus 6 watts equals to 12 watts. 7.2 Applications and troubleshooting parallel circuits. Parallel circuits are found in the home and industry alike. They allow the remaining bulbs and strings of lights to stay lit when one bulb burns out, and they allowed for computers to work on many parts of a problem at one time. Applying Ohm's law to parallel circuits. Ohm's law can be applied to the individual components of a parallel circuit to find unknown values such as current. The total circuit resistance in a parallel circuit is always equal to the source voltage divided by the sum total of the individual resistor current. An example is shown in figure 7-10. You can see that the total of the individual circuit currents, or current 1 plus current 2 plus current 3, equals to 6 amperes. The source voltage of 12 volts is divided by the 6 amperes. The total resistance is found to be 2 ohms. Troubleshooting a parallel circuit. A parallel circuit, the voltage is the same everywhere in the circuit.
Checking
voltage drop is not a very practical method for finding a bad component. One method of finding a problem is by comparing a total resistance reading taken with an ohm meter to the calculated total resistance value. Looking at figure 7-11, we can see that the total resistance value of the ohm meter is 20 ohms. The calculated resistance value is 10 ohms, or 20 ohms divided by 2. Using a little deduction, we can determine that one of the resistors is open. If one of the resistors was shorted, it would cause the fuse to blow. Another method of
troubleshooting
uses current readings taken at each resistor location. First, the total current for the circuit is calculated. Then this value is verified with an ammeter. See figure
7-12.
Using an ammeter, a current reading can be taken across an open
switch.
This reading is then compared to the calculated total current. An open resistor would draw no current, while a good resistor would. In figure 7-13, troubleshooting a parallel circuit will become easier as we learn more about the current, voltage, and resistance characteristics. One factor that assists us in determining the best method to troubleshooting a circuit is determining how the circuit has been assembled. When a breadboard is used to construct circuits, troubleshooting is much easier than when the components are soldered in place and we must first desolder to take the readings. In addition, desoldering components can damage them, giving the technician an even more difficult troubleshooting problem. The technician may believe the problem has been located and corrected only to find another defective component. Unfortunately, the additional defective component may have been damaged while desoldering the component in order to obtain a meter reading. And now review questions for section 7.2. A parallel circuit consists of 3 resistors. All 3 resistors are 20 ohms.
If the current
through the third resistor is 7 amps, what is the source voltage? And we work that problem out on the right side. Number 1, we draw out the circuit. We have 3 20 ohm resistors, and we know resistor number 3 has 7 amps. And since the voltage total equals to voltage 1 equals to voltage 2 equals to voltage 3, that is at each resistor point, then voltage drop at resistor 3 equals to voltage total. This is for a parallel circuit. So to find voltage drop at resistor 3, voltage drop at resistor 3 equals to the current at resistor 3 times the resistance at number 3. Remember, this is the Ohm's law formula with different resistor number. So it's simply voltage equals current times resistance. In this case, 7 amps that we are given times 20 ohms equals to 140 volts. Number 2,
checking voltage drops,
is an fill-in-the-blank method of troubleshooting a parallel circuit, and we are shown the answer on the right side is an impractical method for troubleshooting the parallel circuit.
In summary,
a parallel circuit provides more than one path for current to flow. In a parallel circuit, the voltage is equal throughout the circuit, like voltage total equals to voltage 1
equals to voltage 2 equals to voltage 3, and so on.
Kirchhoff's current law
states that
the total current entering a junction or parallel circuit is equal to the current leaving that junction or parallel circuit. The total circuit current value in a parallel circuit is equal to the sum of the individual current values.
Same as
current total equals to current 1 plus current 2 plus current 3, and so on. The total current resistance is always less than the smallest resistance value in the parallel circuit. That's an important point to remember. And the total power consumed in the circuit is equal to the sum of the individual
power consumptions,
like power total equals to power 1 plus power 2,
and so on.
Remember, power is always measured in watts.
Chapter 7 Review: Parallel Circuits.
A parallel circuit is a circuit that has more than one path for the current to flow, figure 5.5. In this type of circuit, the current can continue to flow through the other if one of the resistors is removed. Voltage in a parallel circuit is equal to source voltage. This means if we were to apply 15 volts to the circuit in figure 5.5, both resistors would read 15 volts on a voltmeter. Current, on the other hand, is additive because you have multiple paths. A little hint to help you remember this is that voltage and current are exactly opposite in a parallel circuit than they are in a series circuit. Figure 5.6. The current in each line of the parallel circuit is called a branch current. Therefore, R1 is one branch and R2 is the other branch. The total of the two branches is called the mainline current or total circuit current. Resistance in a parallel circuit can be found 4 different ways. We will discuss the first 3 ways because they are the most used methods in the industry. You can refer to your textbook for knowledge of the graph method. Try to use the method that is most comfortable to you. The 4 methods are product over the sum, reciprocal method, equation resistance method, and the graph method. We will use figure 5.6 for this discussion. The product over the sum method can be used when there are 2 resistors connected in parallel with different values. The formula is RT equals to R1 plus R2 divided by R1 plus R2. So if we change the values in figure 5.7 to R1 equals R4 and R2 equals 2, then RT equals 3 times 6 divided by 3 plus 6, which is RT equals to 18 over 9, or 18 divided 9, which is RT equals to 2. The next method we will discuss is the reciprocal method. This method can be used when there are 3 or more resistors connected in parallel, figure 5.7. The formula for this method is 1 divided by RT equals to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. If we plug in the values from figure 5.7 into the equation, it will read 1 divided by RT equals to 1 divided by 100 plus 1 divided by 100 plus 1 divided by 100, which is equal to 1 divided by RT equals to 0.01 plus 0.01 plus 0.01, which is equal to RT is equal to 1 divided by 0.03, which is RT equals to 33 ohms. The final method is the equal resistance method. This method can be used when a circuit has 2 or more resistors of the same value, figure 5.8. The formula for this method is RT equals to R divided N. R equals to the ohmic value of resistors, and N is the number of resistors. Looking at figure 5.8, we can plug in its value to this formula. RT equals to 10 divided 2, which is RT equals to 5. Power in a parallel circuit is the total of each branch circuit power added together. The formula to find power in each branch is P total 1 equals to ER1 times IR1. Referring to figure 5.9, we can plug in the values. PT1 equals to 50 volts times 5A equals to 250 watts. Now if you do this for each branch and add them together, you will get the power total for the circuit. If you were to remove any one of these known values, like figure 5.9, you could use Ohm's law to solve for the unknown value. I keep bringing up Ohm's law because it is the main key to solving most electronic equations. It is the beginning of your career. You should know it like the back of your hand. Troubleshooting in this type of circuit, figure 5.9, is best done with power off. It is a resistance check, or what most electronic specialists call a cold check. You are simply checking to see if any of the resistors are open. You can also do a current check on each line because an open resistor will show no current. A voltage check will not help you in this case because each line is already reading source voltage.
Test your knowledge questions.
We'll work these out. Number 1, what is the total circuit
Resistance of a 2 10 ohm resistors
connected in parallel? And we work that out on the right side. We simply use the formula of
2 equally valued resistors.
Remember, it could be more than 2, but in this case there are
2
10 ohm resistors. So resistance total equals to R divided
10.
So we have
10
ohms divided 2.
Resistance total equals to 5 ohms. Question 2.
What is the total resistance of a 12 ohm and a 8 ohm resistor connected in parallel? On the right side, lower left, we have to use the product over the sum formula for resistance. So we have 12 times 8 divided by 12 plus 8 gives us 96 divided 20, or
simplified to
24 divided 5, which is 4.8 ohms. And this is because we have 2 different resistances. We have to use that formula.
The product over the sum formula for resistance.
Number 3, solve for the unknown values in the parallel circuit below. We have a circuit with a 90 volt total voltage or source voltage.
In a parallel circuit, total voltage equals each individual branch voltage.
So your voltage total equals to your voltage drop at branch 1, voltage drop at branch 2, voltage drop at branch
3.
Each branch voltage drop equals total voltage. That's a good point to remember. So working out the problem, we start at the top right of the screen
to
find our resistances.
We are given the resistances,
but we need to find our resistance total. For that, we use the reciprocal method, the reciprocal formula method for resistance, and that is 1 over
RT, or resistance total,
equals to 1 over R1 plus 1 over R2, etc. In this case, we have 1 over 15 ohms on R1. We plug that in as a reciprocal fraction, plus
1 over 6 ohms.
We take that from R2, plus 1 over 10
ohms, which we take from R3.
Which gives us 2 over 30 plus 5 over 30 plus 3 over 30. That's the least common denominator. shown again on step 3.
Top right in the screen.
Which gives us a total of 10 over 30.
Which is simplified to 1 over 3 or 1/3.
So that can simplify further.
Because we have to take the reciprocal of that, which is 3 over 1 or 3 ohms.
To find our current total, we must find the current at each resistor. So we begin with resistor 1 or IR1 as shown on your screen, right side, lower right. So IR1 or current at R1 equals to voltage at R1 or ER1 divided by resistance number 1. And that would be 90 volts divided 15. Now, where do we get our 90 volts for the voltage drop at resistor 1? We know that 90 volts is our source voltage, and it must be the same as resistor 1 or resistor 3 or resistor 2 for that matter. So we know that 90 volts is our resistor voltage drop. Divide that by 15 ohms, which we already know from the problem at R1. So that gives us 6 amps for the current at R1. Moving on to current at R2, we have our voltage drop at R2 divided by R2 resistance, which is 90 divided 6, which gives us
15 amps.
So current flow at R2 is 15 amps. Moving on to current at R3, voltage is 90 volts divided the resistance at R3. We have 90 volts for that also. Our resistance is given as 10, so 90 divided 10 is equal to 9 amps at the current flow at R3. Now we have our I total, which is I total equals to current flow at resistor 1, current flow at resistor 2, current flow at resistor 3, and we have all of those three. We just got those, which are 6, 15, and 9. Add those up, you get 30 amps. We move on to your power total, and it's simply power number 1 plus power 2 plus power 3. To find our power at 1, we simply multiply voltage drop times our current at
resistor 1.
And we have those two values, 90 volts and 6 amps multiplied 540 watts. For power number 2, we have 90 times 15 amps, 90 volts times 15 amps, that's
1350 watts.
1350 watts. At P3, voltage drop at resistor 3 times the current flow at resistor 3, which is 90 volts times 9 amps or 810 watts. And again, down below we show that there is a 90 volts drop at
each
resistor location. Solve for number 4. We follow a similar
step.
We take what we're given and we use that to plug into whatever formula we deem necessary to solve for the problem. We begin with resistance total, and for the resistance total, we have to use the reciprocal formula for resistance because we have
different
resistance values. We're given 3 resistance across a parallel circuit, and instead of voltage, this time we're given total current
for the
circuit or mainline current,
which is 3 amps.
What we know is that total voltage should be the same across each branch of the
parallel circuit,
and total current should be
additive.
It adds at each branch of the circuit. Each branch of the circuits added together
to
give us our total current.
So first, we need to find our resistance total,
which in this case, we write it as 1 over 30 ohms.
We're given that at R1.
Plus 1 over 15 ohms, we're given that as R2. Plus 1 over 10 ohms, we're given that as R3. We add those, we find a least common denominator, 30, and we come up with 6 over 30, which is simplified to 1 over 5 or 1/5, which is further simplified. Remember, you have to flip the reciprocal, 5 over 1 or 5 ohms. To find our voltage total, we simply use Ohm's law, which is voltage equals to current times resistance. In this case, voltage total equals to current total times resistance total. We know our resistance total. We just got that, 5 ohms. We know our current total. We're given that in the problem, 3 amps. So we multiply 3 amps times 5 ohms, which gives us our voltage total,
15 volts.
Further, we need the power total. That's the third requirement from our problem. To work that out, we simply use the power formula or the power equation, which is power equals current times voltage, or power total equals current total times voltage total. And in this case, we already know the current total and the voltage total. 3 times 15 equals 45 watts, or 3 amps times 15 volts equals 45 watts.
To
find our current at R1, We don't have that just yet. They're not given to us in our problem. However, we know the voltage at R1. The voltage is the same across each of the resistors in a parallel circuit. So we know the voltage drop at R1. We know our voltage total is 15. So we plug it in. We know our resistance value that's given to us. So 15 volts divided
30,
which you have to use the Ohm's law formula to solve for current, which is current equals voltage divided resistance, or current at R1 equals to voltage drop at R1 divided the resistance value at R1, which in this case is 15 volts divided 30 ohms, or 0.5 amps. Same steps taken at current at R2, which is voltage drop at R2 divided resistance at
R2,
which again is 15 volts divided by, in this case, 15 ohms, which is given in the problem, equals to 1 amp. Same steps are taken for the current at R3, which is power drop at R3 divided by resistance at R3, which is 15 volts divided
10 ohms,
which is 1.5 amps. For question number 5, in a parallel circuit containing a 4 ohm, a 5 ohm, and a 6 ohm resistor, the current flow is, it's already marked, the highest through the 4 ohm resistor. And we work that problem out just to verify it. We draw out the circuit. We have a parallel circuit with 3 resistors, R1, R2, R3. R1 is 4 ohms, R2 is 5 ohms, R3 is 6 ohms. We have a 10 volt total voltage or source voltage, and we plug in 10 just to test. We did not know the voltage at the source, but we put in 10 just to test out our theory that the highest current goes through the lowest value resistance. And for the current at R1, we plug in the voltage drop at R1 divided by the resistance at R1. This is just simply the Ohm's law formula, Ohm's law equation. Remember, voltage is the same at each resistance location on a parallel circuit, the same as your source. So we know it's 10 volts at R1 divided by 4 ohms. We're given that. So we get 2.5
amps
of current at R1. Let's plug in the same 10 volts at the voltage drop at R2 to get the current at R2. So 10 volts divided by 5 ohms equals to 2 amps. So we have a higher value resistor at R2 and we get a lower current of 2 amps. We have a lower value resistor at R1, 4 ohms, yet we get a higher amperage, slightly higher current at R1, 2.5 amps. So that proves and shows us that the lower the resistor value, as long as your voltage source remains the same, the lower the resistor value, the more amperage you can push or pull through that resistor. And that is the end of the chapter 7. Thank you very much.